Hello and welcome to this video on stationary points. The stationary point is where the gradient is zero, i.e. f-x is equal to 0. Now we're interested in local maxima and local minima. A local maximum is so called because it's the function's largest output within the vicinity. And if you look at the diagram, you can see that we have a cubic graph. The local maximum is f-x is equal to 0, but so is the local minimum, where f-x is also equal to 0. So our first worked example, find the coordinates of the turning points of y equals x cubed plus 6x squared minus 135x. So we differentiate, which gives us 3x squared plus 12x minus 135. And because we find turning points when f-x equals 0, we put that equal to 0. That gives us a quadratic equation which we can divide by 3 and factorize. And then when we solve it, we get x equals -9 or 5. Again, we're looking for coordinates. So if we substitute our x values back into the original curve, when x is -9, we get y equals 972. And when x equals 5, we get y equals -400. So our turning points are -9, 972 and 5, -400. In our second worked example, we're asked to find the least value of f of x equals x squared minus 4x plus 9, which in a sense is the same as finding the turning point of the graph, which again you met this at GCSE. So for method 1, we can use differentiation, which gives us f-x equals 2x minus 4. We put that equal to 0 and solve to get x equals 2. And then we want the least value of the function, so we work out f of 2, which is equal to 5. That is the least value of that function. Method 2 is what we would have done at GCSE, where we complete the square. So we can rewrite it as x minus 2 squared minus 4 plus 9, which in turn becomes x minus 2 squared plus 5, and that has a least value of 5. Notice that method 2 is only applicable for quadratic functions, and for others we have to use differentiation. For our next worked example, we've been asked to find the turning point of y equals root x minus x. So we start by writing that as y equals x to the half minus x, which we differentiate. That gives us a half x to the minus half minus 1 is 0. If we solve that, we get 2 root x equals 1. So root x is a half, and then squaring both sides, we get x is equal to a quarter. And when x is a quarter, y is also a quarter. So the turning point of that curve is at 1/4, 1/4. As well as turning points, there's also a third type of stationary points called a point of inflection, where the curve changes from convex to concave or vice versa. The line curves in one direction before the point of inflection, then curves in the other direction after. If you look at the diagram on the left, we can see concave, which is a bit like a negative quadratic, looks a bit like a cave, and then convex is like a positive quadratic. So in the diagram on the right, which is our cubic graph, it's concave as we move from left towards our point of inflection, where f-x equals 0, and then it's convex afterwards. Note that not all points of inflection are stationary points, as can be seen in an example on the right, which is the diagram in black, which again is a type of cubic graph, but this time at the point of inflection, the gradient is not 0. A point of inflection which is a stationary point is known as a saddle point. So given that we have turning points and points of inflection, how do we tell what type of stationary point we have? Well, the first method is to look at the gradient either side of the point, just before and just after it. So looking at our yellow squiggly curve, as we travel from left to right, the first stationary point we encounter is a local minimum. And we can see that the gradient just before it is negative, the gradient at the point is 0, and the gradient just after it is positive. Moving further along till we get to our next stationary point, that is a point of inflection. The gradient just before it is positive, the gradient at the point of inflection is 0, although we've just seen on the previous slide that the gradient doesn't have to be 0 at the point of inflection. And the gradient just after it is positive again. And then moving again to the right, our local maximum. The gradient just before it is positive, the gradient at the point is 0, the gradient just after it is negative. So bearing in mind that this diagram is not completely accurate in terms of telling you exactly what to do, The thing we need to notice is that for the minimum and the maximum, the gradient is changing from negative to positive or positive to negative either side of the point. Whereas for the point of inflection, the gradient is still positive after you've travelled through it. It was positive before, it's positive after. Or if it was going in the other direction, it could be negative before and negative after. But the fact is the sign has not changed. It's still positive either side of that point. So here's a worked example using that method. Find the stationary point on the curve with the equation y equals x to the 4 minus 32x and determine whether it's a local maximum, a local minimum, or a point of inflection. So dy by dx is equal to 4x cubed minus 32. We put that equal to 0 and solve it, and we get that x is 2. And then to work out what y is, we substitute 2 into the equation. 2 to the 4 minus 32 times 2 is negative 48. So we have a stationary point at 2, negative 48. Now we need to determine which type it is. So we look at the gradient either side. So for example, we could use 1.9 and 2.1 as values of x either side of our x equals 2. When we substitute 1.9 into the gradient function, we get negative 4.564, which is of course negative. And when we substitute 2.1 into our gradient function, we get 5.044, which is positive. And then relating that back to the earlier slide, the gradient on the left is negative. The gradient at the point, as we know, is 0. The gradient after the point is positive. So that is a local minimum. The second method is to use the second derivative. So recall that the gradient gives us a measure of the rate of change of y, i.e. how much the y value changes as x changes, and thus by differentiating the gradient function, the second derivative tells us the rate at which the gradient is changing. Thus, if the second derivative is positive, the gradient is increasing, and if the second derivative is negative, the gradient is decreasing. So at a maximum point, we can see from the diagram that as x increases, the gradient is decreasing from a positive value to a negative value, and hence the second differential is negative. And similarly, at a minimum point, the second differential would be positive. In summary, if we have a stationary point where x is equal to a, then if f double dash a is greater than 0, that's a local minimum. If f double dash a is less than 0, that's a local maximum. And if f double dash a is equal to 0, it could in theory be any type of point. So we resort back to method 1, where we check the gradient either side. And we're going back to this worked example with a stationary point of 2 minus 48 at y for y equals x to the 4 minus 32x. And we're now going to use the second derivative to classify the stationary point. So differentiating it, again, we get 4x cubed minus 32. The second derivative is 12x squared. And if we substitute 2 into that, then we're obviously going to get a positive value. Therefore, that is a local minimum. We're going to finish off by looking at sketching graphs. In the Graphs and Transformations chapter, we use features such as intercepts with the axes and the behavior of the graph as x tends to infinity or negative infinity in order to help us sketch a graph. And now we can also find the stationary points. So the worked example from the textbook says, by first finding the stationary points, sketch the graph of y equals 1 over x plus 27x cubed. So firstly, let's write that with indices. So y equals x to the minus 1 plus 27x cubed. We differentiate it, put it equal to 0. We get negative x to the minus 2 plus 81x squared equals 0. If we rearrange that and solve it, we end up with x being the fourth root of 1 over 81, which is plus or minus a third. Substituting plus or minus a third back in for y, we get that y is either 4 or negative 4. So our stationary points are 1/3, 4, and negative 1/3, negative 4. And we could, of course, also use our second derivative to determine what types of points they are. It turns out that 1/3, 4 is a local minimum, and -1/3, minus 4 is a local maximum. We can also investigate what happens as we tend to infinity. So as x tends to infinity, so does y. We've got 27 infinity to the power of 3. 1 over infinity is essentially 0. And as x tends to negative infinity, y also tends towards negative infinity. X isn't defined as 0 because we've got 1 divided by x, so x equals 0 is an asymptote. But as x tends to 0 from above, y tends to positive infinity, and as x tends to 0 from below, y tends to negative infinity. And taking all that together, we can sketch the graph as shown. Thank you very much.